Good afternoon, ladies and gentlemen. I am honored to be among you today to present my research on a topic that holds significant promise for the healthcare industry: IoT-Powered Predictive Maintenance Framework for ICU Ventilators. As we all know, intensive care unit ventilators play a critical role in saving lives, especially during times of crisis. However, ensuring the reliability and optimal performance of these life-saving devices is a constant challenge for healthcare facilities worldwide. Throughout this presentation, I will guide you through the key components of our framework, highlighting its potential impact on healthcare delivery and patient care. But before delving into the specifics, allow me to provide some context on the pressing need for such innovation in the realm of medical equipment maintenance. Thank you for your attention, and without further ado, let us begin. During these last years, the landscape of healthcare is continuously evolving, with rapid advancements in medical equipment playing a pivotal role in enhancing patient care and improving health outcomes. From state-of-the-art imaging devices to life-sustaining ventilators, these innovations have become indispensable assets in modern healthcare facilities. However, these advances are accompanied by a pressing need for meticulous maintenance to keep these devices in a good functioning state. Consequently, healthcare facilities face the significant challenge of efficiently managing a wide range of equipment. Any malfunction in critical devices can not only compromise patient safety, but also pose significant financial risks to healthcare institutions. On the other hand, the healthcare industry is undergoing digital transformation, which causes a surge in health data from interconnected devices like IoT and cloud computing. This presents opportunities and challenges, leading to the exploration of new data analytics methods. From this, predictive maintenance emerges as a proactive maintenance strategy that aims to predict when equipment failure might occur so that maintenance can be performed just in time to prevent the failure. The principle behind predictive maintenance is to monitor the condition and performance of equipment continuously by collecting data from various sensors or other monitoring devices installed on the equipment. This data typically includes information such as temperature, vibration, pressure, and other indicators of equipment health. This shift from reactive to proactive maintenance promises improved reliability, safety, and performance, aligning with the goals of quality patient care and financial sustainability. Thank you for your attention during the introduction. Now let's take a closer look at the structure of our presentation. We have organized our findings into three main sections, each offering valuable insights into our research journey. First, we will be delving into our study case. Here, we will be discussing the objectives driving our research, the specific equipment we've analyzed, the detailed analysis conducted through the failure modes and effects analysis, and finally, the proposed architecture based on our findings. Following that, we will transition into the discussion section. This is where we will be exploring the implications of our research findings. Next up, we will be exploring the opportunities and challenges arising from our study. So, our study is centered on the creation of an IoT-based architecture for predictive maintenance of ICU ventilators. We will be specifically working on the Carescape R860 ICU ventilators. So, before talking about our subject, let's see the importance of ventilators in the medical field. These ventilators play a vital role in patient care due to their extensive use in critical medical scenarios. Given their crucial function in supporting patient respiratory needs, any malfunction in these devices can have severe consequences, underscoring the critical importance of ensuring their optimal performance. ICU ventilators are known to be lifelines for patients who rely on them for extended periods, making their proper functioning absolutely essential for patient safety and well-being. Our study recognizes the imperative need for continuous monitoring of these ventilators to prevent errors and potential hazards that could jeopardize patient health. Therefore, we will be aiming to present an IoT-based architecture of predictive maintenance for the Carescape R860 ICU ventilators. In order to conduct our research, we will be working on a group of Cariscape R860 ICU ventilators across various medical centers. Now let's have a look at the general description of these devices. So the Cariscape R860 is a system that integrates cutting-edge technology with an intuitive user interface, ensuring ease of use. It contains adjustable icons, enabling access to historical trends, patient status, and clinical decision support. It offers extensive performance options for user configuration. It also provides a comprehensive solution covering ventilation, monitoring, and connectivity, with a full touch screen for quick information access and procedures. It can be used for adult, pediatric, and neonatal patients. Next up, we will have a look at the ventilation unit. So the ventilation unit is positioned beneath the user interface screen. This component is outfitted with crucial ports designed for seamless attachment of breathing circuit accessories. Another component of these ventilators is the pneumatic circuit. This component serves the critical function of supplying gases to the patient, drawing from the compressed air and oxygen sources to ensure continuous respiratory support. Notably, it incorporates distinct inspiratory channels, allowing for precise control over oxygen levels to meet individual patient requirements effectively. We also have the electronic circuit. This component assumes the crucial role of controlling and fine-tuning the pneumatic system, ensuring optimal performance and patient safety. In this slide, we will be stepping into another step of our study. We will be delving into the critical process of failure mode and effect analysis, sometimes known as failure mode effects and criticality analysis. This method is our strategic tool to pinpoint the most vulnerable components of the ventilator, ensuring meticulous monitoring and preemptive maintenance. Through this analysis, we will be identifying these weak points, and then we can proactively implement measures to mitigate risks, safeguarding patient safety and optimizing the reliability of the ventilator system. In our analysis, we assign a criticality rating of C. In our analysis, we assign a criticality rating of 18 to the pneumatic block, signifying its paramount importance within ICU ventilators. This designation underscored the indispensable role of the pneumatic block in ensuring optimal ventilator function and consequently patient well-being. In our analysis, we assign a criticality of 18 to the pneumatic block. This designation underscores the indispensable role of the pneumatic block in ensuring optimal ventilator function and consequently patient well-being. At the heart of this critical component lies the compressed air filtration chain, a vital system responsible for delivering clean and precisely regulated air to patients undergoing ventilation. The integrity of this filtration chain is important, as any compromise in air quality or pressure regulation could have severe consequences for patient respiratory support. Therefore, it is essential to meticulously monitor and maintain the pneumatic block in a good functioning state, particularly the compressed air filtration chain. To understand this failure more, in this slide we will be talking about the issue that can arise in the air filtration chain. So humidity of compressed air can lead to reduced filtration efficiency, component corrosion, and potential ventilator malfunction. During the compression process, atmospheric air undergoes cooling, causing water vapor condensation. This excess moisture compromises filtration mechanisms, accelerates component corrosion, and increases the risk of internal malfunction. To mitigate this risk, it's essential to manage humidity level within the compressed air system effectively. Implementing humidity control measures, conducting regular maintenance checks, and establishing monitoring protocols are key steps in addressing this issue. Now I will be introducing the predictive maintenance system architecture that encompasses 4 layers. This architecture serves as the backbone of our system or our strategy, providing a structured framework for proactive equipment management. So next up in our presentation, we will be presenting each layer specifically. In our predictive maintenance system architecture, the first layer serves as the input layer, tasked with gathering essential data for analysis. At its core is the DHT22 sensor, a cost-effective yet highly efficient digital temperature and humidity sensor. This sensor, equipped with a capacitive humidity sensor and a thermistor, meticulously monitors airflow and provides digital signal output through its data pin. Operating at a rapid interval of every 2 seconds, it delivers real-time information crucial for our predictive maintenance framework. Installed within the air filtration chain of the ICU ventilator, the DHT22 sensor plays a pivotal role in assessing the performance of the pneumatic block. The data it collects, comprising humidity levels measured at various time intervals, is then transmitted to the fog layer via the Constraint Application Protocol (COAP), facilitated by the ESP32 microcontroller functioning as a gateway. This seamless integration of sensors and communication protocols forms the foundation of our predictive maintenance system, enabling proactive monitoring and timely interventions to ensure optimal equipment functionality and patient safety. The second layer, called fog computing, acts as a bridge between the ventilators with DHT22 sensors and the central cloud server. Its role is to enhance the efficiency, responsiveness, and scalability of our predictive maintenance system. Here's how it does it. Centralized data processing and filtering. It gathers and organizes data from the ventilators, making it easier to manage and analyze. Local anomaly detection and classification. It can spot any unusual patterns or problems in the data coming from the ventilators and categorize them for further investigation. Bandwidth optimization. By handling data processing locally, it reduces the amount of data that needs to be sent to the central server, saving bandwidth and speeding up the process. Lastly, edge machine learning for quick decision making. It uses machine learning algorithms to quickly analyze data and make decisions at the edge, without needing to send everything to the central server. This helps in detecting and addressing issues promptly. The next layer is the cloud computing layer that serves as the core infrastructure for storing, processing, and analyzing data centrally. Here's how it does it. Real-time data handling. It manages the flow of data from the predictive maintenance system, ensuring it's processed and stored promptly. Second, cloud-based analytics. It conducts in-depth analysis of the data collected, providing valuable insights into the performance of the CareScape ICU ventilators. Third, remote maintenance insights. It offers remote access to maintenance insights, allowing for timely interventions and troubleshooting. Lastly, security measures. It implements robust security measures to safeguard sensitive healthcare data, ensuring compliance with privacy regulations and protection against cyber threats. Finally, we have the output layer. The output layer acts as the interface for technicians and incorporates machine learning for predictive maintenance. Here's how it does it. First, interface for technicians. It provides a user-friendly interface for technicians to monitor ventilator health. It alerts technicians when humidity levels approach dangerous thresholds, prompting preventative maintenance actions. Second, machine learning implementation. It initially uses supervised machine learning, where technicians report malfunctions to train the algorithms, allowing for reactive decision-making. The system then progresses to semi-supervised and unsupervised machine learning methods for more autonomous operation. Lastly, evaluation of methods. The effectiveness of fault classification, anomaly detection, and real-time prediction is continuously assessed for each machine learning method, ensuring optimal performance and reliability. After presenting our architecture, now we will be delving into the discussion part. The framework selection for our predictive maintenance system was based on its ability to centrally manage various ventilator models, particularly the CareScape. Here's what makes it unique. First of all, we have the centralization. Our system effectively centralizes predictive maintenance for different ventilators, specifically tailored for the CareScape model. Second, we have the humidity monitoring integration. We've integrated a humidity monitoring system into the medical air filtration process to address potential issues related to humidity, a critical factor in the ICU ventilator malfunctions. Third, the IoT-based predictive maintenance. By leveraging IoT technology, our system gathers real-time data from multiple CareScape ventilators, providing comprehensive and flexible equipment monitoring. Fourth, we have the distinctiveness of our design. Our approach stands out for its combination of IoT, fog computing, and cloud computing technologies in predictive maintenance. It features a well-defined four-layer structure covering centralized management, humidity monitoring, and real-time analytics. Additionally, it integrates adaptive threshold techniques, focuses on local processing via fog computing, and utilizes machine learning models. Last, it is a comprehensive approach. Overall, our system offers a more comprehensive and innovative approach to enhancing the safety, reliability, and performance of critical medical equipment in healthcare settings. It builds upon previous research efforts to provide a robust solution for predictive maintenance. Now, we will be having a look at the opportunities and challenges of our framework. Concerning the advantages, our predictive maintenance system offers several of them. First, improved healthcare management. By providing a unified platform for analysis and proactive maintenance, our system enhances healthcare management. Then we have the unified analysis and proactive maintenance. It enables unified analysis of ventilator data, facilitating proactive maintenance to prevent potential malfunctions. Real-time monitoring and communication. With real-time monitoring capabilities, our system ensures timely communication of critical information to healthcare providers. It is also a versatile solution. Our system is versatile and adaptable to various medical equipment setups and configurations. It is a streamlined predictive maintenance. Through automation and predictive analytics, our system streamlines the predictive maintenance workflow, optimizing equipment performance. On the other hand, our architecture faces several challenges that need to be addressed. First of all, we have technical complexity. Implementing and managing the technical infrastructure of the system can be complex and requires expertise. Ethical implications. Ethical considerations regarding patient data privacy and consent need to be carefully managed. We have also security challenges. We have to ensure the security of patient data and system integrity against cyber threats. Embedded system integration. Integrating our system with existing embedded systems in medical equipment requires meticulous planning and coordination. Finally, we have the human factor. The effectiveness of the system also depends on human factors such as user training and adherence to protocols. In summary, this article introduced a state-of-the-art real-time monitoring system tailored for ICU ventilators in diverse healthcare settings. With the surge in both the quality and quantity of medical devices, traditional maintenance methods may no longer suffice. The proposed architecture empowers technicians to monitor ventilator health status, predict maintenance needs, and schedule tasks promptly, leveraging data analysis and live notifications. By using big data and IoT, it swiftly detects and communicates critical events, emphasizing the significance of humidity monitoring for product quality. Looking forward, the aim is to enhance the system with an integrity monitoring framework for a comprehensive predictive maintenance approach, ultimately elevating patient care standards. Thank you for your attention.